7 minutes ago, in a quiet corner of infrared data collected by the most powerful telescope humanity has ever built, astronomers confirmed something that should not exist. Not a planet, not a galaxy, a structure, a massive, gravitationally bound structure sitting at the very edge of time itself, so early in the universe's history that by every model we trusted, it simply should not have had time to form. This is the story of the James Webb Space Telescope's most disruptive discovery yet, a find that is quietly forcing physicists to ask whether everything we thought we understood about how the universe built itself is wrong. And by the end of this video, you are going to understand why some of the smartest people on this planet are looking at this data and admitting they do not have a clean explanation for it. Let's start with what this thing actually is, because the name alone, JWST, does not do justice to what it represents. In late January 2026, a team of astronomers, using both the James Webb Space Telescope and NASA's Chandra X-ray Observatory, announced the discovery of a protocluster of galaxies, existing when the universe was only about 1 billion years old. To put that in perspective, the universe today is roughly 13.8 billion years old. So we are talking about a snapshot from a time when the cosmos had only lived through about 7% of its total history. Imagine trying to understand the entire life of a 90-year-old person by looking at a single photograph taken when they were 6. That is the kind of leap backward in time we are dealing with here. And inside that impossibly young snapshot, astronomers found something enormous already sitting there, fully formed enough to be unmistakable. James Webb's infrared imaging picked out at least 66 potential member galaxies, all clustered together in a relatively small patch of sky, all likely bound to one another by gravity. On its own, that would already be a notable find. A crowd of 66 young galaxies huddled together this early in cosmic history is rare, but it's what Chandra found surrounding them that turned this from an interesting observation into a genuine anomaly. Chandra detected a vast cloud of superheated gas wrapping around the galaxy group, gas reaching temperatures of millions of degrees, hot enough to glow in X-rays. That kind of extreme heat does not appear randomly in space. It is the signature of matter being violently compressed, of gas falling inward under enormous gravitational pull and being shocked to unimaginable temperatures as it collides with itself. In other words, it is the fingerprint of a structure that is not just sitting quietly in the young universe. It is actively assembling itself, caught in the act of construction, gravity visibly at work pulling mass together into something bigger. Astronomers calculated the total mass of this system at roughly 20 trillion times the mass of our Sun, 20 trillion solar masses, sitting there, fully in motion, just 1 billion years after the Big Bang. Now here is why that single number is causing so much quiet panic in cosmology circles. Under the standard model of how the universe evolved, the model that has guided astrophysics for decades, structures like this, true galaxy protoclusters complete with X-ray emitting hot gas, are not supposed to exist until the universe is at least 2 to 3 billion years old. That is not a rounding error. That is astronomers finding something that, according to the textbook timeline, needed twice as much time, maybe 3 times as much time, to come into being. And yet here it is, already at that advanced stage of formation, a full 1 to 2 billion years ahead of schedule. One of the lead researchers behind the discovery put it about as plainly as a scientist ever does in a formal paper, essentially saying the universe seems to have been in a hurry to grow up. That phrase captures the unease perfectly, because if the largest gravitational structures in the cosmos can assemble this quickly, then something about our understanding of how the universe built itself from nothing but hot, uniform plasma into galaxies, clusters, and eventually planets and people, is incomplete in a way that actually matters. And here is the part that should really make you sit up. JWST is not an isolated anomaly. It is not one strange image that slipped through and got overhyped. It is part of a pattern that has been quietly stacking up, discovery after discovery. ever since James Webb opened its golden mirror to the cosmos back in 2022. Let's walk through some of the other pieces of that pattern, because once you see them side by side, the picture gets a lot harder to dismiss as coincidence. Just a few months before the JWST announcement, in a completely different region of the sky, astronomers using Webb spotted a colossal spiral galaxy that their research team nicknamed the Big Wheel. This galaxy existed only about 2 billion years after the Big Bang, still incredibly early in cosmic history, and yet it was already roughly 5 times more massive than our entire Milky Way galaxy. Not a small, chaotic smudge of infant starlight. A vast, fully organized rotating disk, complete with clearly visible spiral arms. The kind of structure normally associated with mature, settled galaxies billions of years older. According to standard models of galaxy formation, a disk that large and that massive, forming this early, should have been a mess. The early universe was a violent, turbulent place, full of gas clouds slamming into each other, galaxies merging chaotically, everything churning and disorganized. A graceful spiral pattern is what happens after things calm down, after a galaxy has had time to settle into a stable rotation. The Big Wheel was not supposed to have had that time. It should have been torn apart, or kept in a state of permanent chaos long before it could organize itself into something this clean. Instead, there it was, spinning calmly, fully formed, far too early. Researchers studying it made an important point that applies to everything we are talking about today. Early, they said, does not mean simple. By the time the universe was only 2 billion years old, some regions had already built genuinely massive, organized structures. Gas was flowing efficiently into galaxies. Stars were forming at a rapid pace. Black holes were growing. Galaxies were actively interacting with their neighbors. The old assumption that the early universe was sparse, primitive, and slow-moving is being replaced by a much messier, much more energetic picture. One where certain pockets of space appear to have found a shortcut to maturity that our models simply did not predict. Around the same time, a separate team using Webb found something almost the opposite kind of problem. And honestly, just as strange. They discovered a massive galaxy from the early universe. One that by all rights should have been young and dynamic. That showed no signs of rotation at all. It was just sitting there, structurally still, behaving the way astronomers normally expect only from very old, settled, extremely mature galaxies found much closer to us in the nearby universe. A galaxy that old and that motionless simply should not exist when the cosmos itself is barely out of its infancy. And yet the data was unambiguous. The lead researcher on that study noted just how surprising it was to see a transformation like that, one that is thought to take an enormous span of cosmic time, show up in a galaxy that formed when the universe was less than 2 billion years old. So think about the contradictions sitting right next to each other in the data. One galaxy, the Big Wheel, is spinning in perfect, organized rotation far earlier than it should be able to. Another galaxy, observed at a similarly early time, has already stopped behaving like a young, dynamic system and looks structurally old. Both of these things are, in their own way, impossible under the old timeline. And both of them are sitting in Webb's data, confirmed, peer-reviewed, published. Then there are the black holes. And honestly, this might be the most persistent thorn in cosmology's side out of everything Webb has found. Webb has now repeatedly detected supermassive black holes, some exceeding 1 billion times the mass of our own Sun, sitting at the centers of galaxies from an era when the universe simply had not existed long enough, according to conventional physics, for a black hole to grow that large. We are not talking about one strange outlier. We are talking about multiple independent observations, multiple separate research teams, multiple confirmations across different fields of the sky. The data keeps agreeing with itself over and over, and it keeps saying the same uncomfortable thing. Massive black holes, fully grown, showing up far earlier than the standard models of black hole growth think should be physically possible. To understand why this matters so much, you have to understand how black holes are thought to grow in the first place. They start small, from the collapse of a massive star or from more. Exotic seed processes still being debated. And then they grow slowly over time by pulling in surrounding gas and dust, or by merging with other black holes. That growth takes time. It is bound by physical limits on how fast matter can actually fall into a black hole without the whole system becoming unstable. Finding black holes already a billion times the mass of the Sun within the first several hundred million years of cosmic history is a bit like finding a fully grown oak tree within days of planting the acorn. Something about the growth process, or the starting conditions, or both, does not match what the equations predict. Even galaxy mergers, the messy business of two or more galaxies crashing together and combining, are behaving strangely in Webb's early universe images. Researchers recently identified a tightly packed group of at least 5 interacting galaxies, actively colliding and merging together, just a few billion years after the Big Bang. And surrounding this cosmic collision was an unexpected halo of oxygen-rich, chemically enriched gas. That enrichment matters, because it means earlier generations of stars had already lived, fused heavier elements in their cores, and died, seeding the surrounding gas with oxygen, before this merger even happened. That is a layered, complex history playing out in a part of the universe that, under older assumptions, should barely have had time for a single generation of stars to form, let alone multiple. Researchers studying this system suggested it may actually help explain another puzzle. Webb has uncovered a growing number of massive galaxies that appear to already be inactive, essentially retired, just a few billion years after the Big Bang. If systems like this one merge rapidly and burn through their gas quickly, they could be the direct ancestors of those strangely dormant, prematurely aged galaxies showing up elsewhere in Webb surveys. It's another thread in the same tapestry. Everywhere Webb looks in the deep past, it keeps finding evidence that the early universe was busier, more violent, and further along in its development than anyone expected. There is more. Astronomers using Webb identified what may be one of the universe's earliest known barred spiral galaxies, a striking structure with an elongated bar of stars stretching through its center, forming just 2 billion years after the Big Bang. This galaxy, catalogued as Cosmos 74706, dates back roughly 11.5 billion years, and a stellar bar like that typically forms only after a galaxy has had significant time to settle into a stable rotating disk. Finding one this early adds yet another data point to the same growing contradiction. And in July of 2026, researchers using Webb went even further, identifying the most distant known nuclear disk ever observed inside a galaxy, a compact, actively forming, rotating structure of stars at the very center of a galaxy seen as it appeared only about 4.5 billion years after the Big Bang. The team behind that discovery explicitly said that Webb's extraordinary resolution keeps revealing that mature galactic structures existed far earlier than anyone previously believed. That sentence alone, mature structures existing far earlier than believed, could serve as the tagline for basically everything we've covered in this video so far. So let's step back and ask the obvious question. What does all of this actually mean? For decades, our picture of cosmic history works something like this. After the Big Bang, matter was spread almost perfectly evenly across space, with only the faintest ripples of density, tiny variations of maybe 1 part in 100,000. Over enormous stretches of time, gravity slowly amplified those ripples. Small clumps of gas collapsed into the first stars. Those stars gathered into the first small galaxies. Those small galaxies slowly merged and grew over billions of years into the large galaxies we see around us today. And only after an extremely long stretch of that slow, patient accumulation would you expect entire clusters of galaxies, structures made of hundreds or even thousands of individual galaxies bound together by gravity, to finally start forming. This was supposed to be a gradual, almost leisurely process on cosmic timescales, taking multiple billions of years to reach the kind of scale that JWST has already reached in just 1 billion years. But Webb keeps finding the end result of that long, slow process showing up far too soon. There are basically three broad possibilities being discussed by cosmologists right now, and none of them are small, comfortable adjustments. The first possibility is that galaxies, black holes, and the larger structures they belong to simply grow much faster than our current models predict, meaning something about the physics of star formation, gas accretion, and gravitational collapse in the early universe needs to be revised, perhaps significantly. The second possibility is that the early universe contained more raw material than we accounted for, more density variation in that primordial soup right after the Big Bang than the standard model currently allows, giving gravity a head start that let structures assemble faster simply because there was more to work with from the very beginning. And the third possibility, the one that keeps cosmologists up at night, is that there is something more fundamental we are missing entirely, some property of dark matter, some behavior of gravity itself, or some entirely new physics in the early universe that current theory does not capture at all. This is the possibility that would not just tweak the existing model, it would require rewriting it. None of these explanations has been proven yet. Researchers are actively debating all three, running new simulations, combing through the data for clues, trying to figure out which piece of the puzzle is actually broken. What has been proven, again and again, across multiple independent research teams, multiple instruments, and multiple completely separate patches of the sky, is that the observations themselves are solid. This is not a single strange image that might be a fluke, a calibration error, or a statistical accident. It has become a consistent, repeating signal. Massive, organized, mature-looking structures keep showing up far earlier in cosmic history than the standard model says they should be able to, and that signal is showing up at the very edge of observable time, buried in the oldest light human instruments have ever managed to capture and decode. This is what makes the James Webb Space Telescope fundamentally different from everything that came before it. It is not simply taking prettier, sharper pictures of familiar things. Its infrared instruments are tuned specifically to catch light that has been stretched and reddened by billions of years of cosmic expansion, light that started its journey when the universe itself was barely out of its infancy. Webb is looking so far back in time that it is effectively watching the universe's earliest days play out in front of it, and instead of finding the quiet, sparse nursery that theory predicted, it keeps finding fully formed skeletons of structures that were supposed to take billions more years to build. So think about what is actually being asked here, because the implications stack up quickly. If a protocluster with 20 trillion solar masses can assemble within the universe's first billion years, if a galaxy 5 times more massive than the Milky Way can hold together in a clean spiral shape after just 2 billion years, if supermassive black holes can balloon past 1 billion solar masses before the universe even reaches what amounts to its toddler years, then what does that say about everything else astronomers assumed about the broader arc of cosmic history? How many more of these impossible early structures are sitting out there right now, hidden in the deepest fields Webb has not pointed its mirror at yet? How many more black holes, spiral galaxies, protoclusters, and merging systems are quietly breaking the same rules in patches of sky no one has examined closely enough to notice? Every new observation from Webb seems to push the earliest known example of some mature structure a little further back in time. And every time that boundary gets pushed earlier, it breaks another assumption that used to feel settled. Each broken assumption is one more clue suggesting that the story of how our universe assembled itself from a smooth, nearly featureless plasma into galaxies, black holes, planets, and eventually into us, still has entire chapters that we have not read yet, chapters that current physics may not even have the vocabulary to describe. We are standing at a genuinely strange moment in the history of astronomy. We built a telescope powerful enough to stare almost all the way back to the beginning of time, and instead of confirming the calm, orderly story we expected, it keeps finding a universe that was already ahead of schedule, already busy, already assembling. Enormous structures on a timeline that should have needed twice as long, sometimes 3 times as long, to happen. The edge of time, the very earliest slice of cosmic history we can observe, keeps turning out to be far busier, far faster, and far stranger than anyone expected going in. And James Webb is nowhere near finished looking. Its science mission still has years left to run. More deep fields still waiting to be surveyed. More of that oldest light still waiting to be decoded. Every one of those future observations is a chance to find another Jade's ID1, another big wheel, another impossible black hole sitting where nothing is supposed to be able to exist yet. So here is the real question I want you to sit with before you go. If the earliest, faintest slice of the observable universe we have examined so far has already produced this many objects that break our timeline, what is Webb going to find in the deep fields still waiting in the queue? What happens when astronomers finally get enough of these early massive structures, catalogued to run real statistics on them, instead of treating each one as a rare, isolated surprise? Is this handful of anomalies the edge of a much larger pattern that will eventually force a genuine rewrite of how we think the universe assembled itself? Or will we discover some more elegant explanation, some overlooked piece of physics that quietly resolves all of it at once? Nobody knows yet. That is what makes this moment in astronomy so exciting. We built an instrument capable of catching the universe in the act of contradicting itself, and it keeps delivering. If this kind of discovery fascinates you, the idea that the deeper we look into the past, the more the universe seems to be rewriting its own timeline in front of us, make sure you are subscribed, because these early universe surprises are only going to keep coming as Webb's survey continues. Drop a comment and tell me which part of this shocked you the most. Was it the 20 trillion solar mass structure forming within the universe's first billion years? The spiral galaxy that should not have survived intact this early? The billion solar mass black holes that grew far too big, far too fast? Or the galaxy that somehow looks old before its time? Let me know down below. And if you want to go even deeper into how astronomers are racing to make sense of the invisible scaffolding holding the universe together, there is another video linked right now that you need to watch.